Swayam Prabha. Digital India. Educated India.
Okay, good morning. So we'll continue with this chemistry of polymers from the last class. So what do we understand by polymers? What does it mean? This word polymer means what? Many units, many parts combined together, right? And then we specifically looked at carbon, because when we look at polymers, general set of polymers, carbon is the more dominant element. And then we looked at some of the electronic structure of carbon atom, and we saw that it has a very a strong affinity to hybridize and form different kinds of orbitals, which can allow sharing of 2 electrons or 4 electrons or 6 electrons with a neighbor. Therefore, it can bond, single bond, double bond, triple bond. So it's very versatile in making bonds with others, and it has a tendency to grow as a linear chain. Okay, so we'll continue from there. And what we discussed yesterday was about something called the primary carbon or the primary bonds. Okay, so if you want to go from here, we see that, okay, yes, carbon is good. Carbon can form bonds with the hydrogen, and it can link into a long chain. If you do that, what happens is you may be able to create a very large molecule. Okay, but you will see it will be very mobile, and it's going to be very flexible, and so on and so. But many of the plastics polymers that we see, they are more harder, rigid. Okay, so if you ask, where this rigidity or the strength comes from, it is because of something called intermolecular forces or secondary bonds. Okay, so that's the context of today's discussion. So the secondary bonds or intermolecular interactions, so these are basically synonymously used. So we say secondary bonds because these are not permanent bonds. Okay, the other chemical bonds, CC bond, single bond, double bond, triple bond, those are chemical bonds, those are primary bonds. Okay, so they're very hard to break. Then there are other sets of interactions which we call them as intermolecular interactions. This means how atoms between chains, between polymer chain interact, or few atoms from the other side of the part of the chain can also interact. Okay, and these interactions are transient. They form and they break, they form and they break. Okay, so that's why we call them as a secondary bond, and they are much weaker. Okay, and this is a reason why when we have this polymer made through these primary bonds, through the secondary bonds and intermolecular interactions, you can actually have more stronger polymeric materials. Okay, so in this discussion, I want to walk you through some aspects of this secondary bonds or intermolecular interactions. This is also reason why even simple systems like, for example, water exist in solid, liquid and gas, right? So you take water and then you freeze it, you can make ice. Melt it, you can make a liquid, and then put more heat, you can vaporize it. In all these 3 forms, the solid, the liquid and the vapor, the chemical nature of water molecule remain intact. Okay, the OH bonds are intact, the primary bonds are intact. What has really changed is the relationship between molecules, how closely they are packed, what is the level of interactions. That's what determines whether the molecule is going to be packed as a solid or as a liquid or as a gas. Okay, as you would know, in the gaseous form, molecules are far apart, the intermolecular interactions are not strong. Whereas in the solid, the molecules are packed tightly, they are sitting very close to each other, there is a very strong intermolecular forces acting between them, keeping them together, and that's why you need heat to break that bond open so that you can make liquefaction. Okay, again in the liquid also, there are still interactions, moderate level of interactions. If you supply more heat, you can even break those weaker bonds, and then you can make it gas. So even for simple systems like alcohol, water and other systems, this intermolecular force is very evident in the way that we deal with them. Okay, so in the same way, when we go to polymers are nothing but long chain molecules, and in those also these intermolecular forces become very, very important in determining the physical state, mechanical properties and etc. Right. So I want to give some thoughts on these aspects primarily related to polymers. Okay, these intermolecular forces are ubiquitous. It is operating for all molecules actually. Okay, but now we will focus on polymers, how these interactions play a role in the polymer systems. So these are the points I'm trying to say. See, the orbital structure sp3, sp2, sp, these allow carbon molecules to form primary bonds, so it can grow chains, long chains. The intermolecular or interchain interactions provide strength in solid phase. So when you make this polymer, and you will see this polymer mostly forms a amorphous or solid object, and the reason for that is that there is a very strong intermolecular or interchain. Inter means between, interchain means between chains there are interactions. Okay, if you don't have those interactions, like I said, you are going to have mostly liquid or a viscous liquid because of very weak interactions. Okay, so it's very important for polymers that the intermolecular forces determine their properties. Now, I want to walk you through certain aspects of this intermolecular forces. There are few kinds, and I'll try to qualify some of them. Okay, the most important one is called this dispersion interactions or dispersion forces, also known as this van der Waals forces. Okay. Now, when we have many molecules which are actually non-polar, okay, when you say non-polar, that means there is no net dipole moment. Okay, so those are called inert molecule or non-polar molecules. Even then, there is going to be some sort of a transient dipole. Okay, on a momentary basis, there is going to be a dipole moment. The next moment will disappear. Okay, so if you do a time average of this dipole moment, it will be 0 because it's a non-polar molecule. However, when you try to look at whenever there is a transient dipole created, when you try to average the interaction between the neighbors, that interaction becomes finite. Okay, and that's what we call as a dispersion interactions. It's a universal interaction, whether the molecule is polar or non-polar or whatsoever, these van der Waals forces are always going to be there. Okay. Now, if you think about this energy scale, these van der Waals forces are very weak. Okay, the energy scale is roughly about 2 to 8 kilojoules per mole. And if you want to compare this with the bond energy that we talked about in the last class, the CC bond, the primary CC bond, single bond interaction, the bonding energy is about 348 kilojoules per mole. Very strong. Compared to that, this van der Waals forces or dispersion forces is very, very weak, right? But it's there. Now, how do we manipulate or how do we change these interactions? Well, if you think about molecules which are larger in size, you can actually have stronger van der Waals forces or stronger dispersion forces. And the reason is, so I'm showing one equation. The derivation of this equation is not important. What is important is to see that this is an interaction energy between two non-polar atoms separated by a distance of r. Okay, so this basically decays as 1 by r power 6. Two things. First, this interaction is always attractive. Okay, atoms want to come close to each other, and the dependence is 1 by r power 6. So when they are far away, they don't interact. Okay, these are called short range interactions. Only when these atoms come close to each other, this net transient dipole interactions become dominant, and it goes as 1 by r power 6. There are a few other terms here. What is important here is to see that there are a couple of terms called the polarizability. Okay, even for non-polar atoms, there is a terminology called polarizability. What it means is, if I have a non-polar molecule, if I apply an electric field, how much I can induce dipole in that. Okay, so that is the polarizability, and these are values that are reported for all the atoms. And then this polarizability actually is proportional to the volume of the atom. It's actually r to the cube. If r is the size of the atom, r cube is proportional to the volume, right? So if you have an atom which is bulkier, bigger, the polarizability will be higher. If the polarizability is very high, then the van der Waals interaction also will be high. So between two molecules, given a choice, if I have a pair of small molecule and a pair of big molecules, you can say that the van der Waals interaction is going to be stronger for the pair having larger molecules. Okay, so you can actually calculate from quantum mechanical theory using this kind of expression the magnitude, for any pair 1 and 2, where 1 and 2 means two different pair. If you know the polarizability and if you know the distance between two atoms, based on other constants here, you can calculate this energy. This energy is likely to be of this order, 2 to 8 kilojoules per mole. Okay. So here I have given an example. So by the way, this van der Waals or dispersion interaction is ubiquitous. It is operatable under all kinds of, even for carbon dioxide, which is a non-polar molecule, there is a dispersion force. Even things like argon and neon, which are inert gases, even then there are van der Waals forces between them also, right? So it's a very ubiquitous, universal forces of interactions. But if you look at how this is operating between polymer chains, so here I have given an example. We are looking at two polyethylene chain. Okay, the top one, this is CH2, CH2, CH2. This is a one part of a big polymer chain. This is another polymer chain, right? And then you can see that the wiggly line that I have shown here, that kind of indicates the van der Waals interactions or dispersion interactions. It is shown as a wiggly line because these are not permanent bond. Okay, if you apply some amount of energy, you can rip off this. You can actually remove this bond. That's why it's called a transient bond or a secondary bond. Okay, so it is not in this particular orientation. We highlight the van der Waals interaction between the hydrogen of this chain and hydrogen of this chain. But suppose in a three-dimensional picture, this chain can take a different conformation. This carbon can also interact with this hydrogen through van der Waals forces. So all atoms, all atom pairs can actually interact via van der Waals forces. Even though in this picture I have shown between H and H, there is between C and C, between C and H, and so on, so right. Any thoughts on this point? You follow? All right. The next one is called the dipole interactions or dipole moments. So this picture kind of tells you what I mean by dipole. So let's say I have a nucleus here, and the electron is somewhere slightly shifted from its equilibrium position. Okay, so there is a separation of charges. The nucleus is somewhere and the electron is somewhere else. The separation of the charges over a small distance will give rise to a permanent dipole. Okay, for example, if you consider HCl, HCl is a molecule. Chlorine wants to attract electron from the hydrogen. So what happens is that there is going to be a slight shift of electron towards chlorine and slight positive charge to the hydrogen. The net separation of these charges will give rise to a permanent dipole. So HCl has a permanent dipole, water has a permanent dipole, right? Carbon monoxide will have a permanent dipole. So if you look at any standard chemistry textbooks, you will see list of compounds with its own dipole moments. These are permanent dipole moments. The previous case what I talked about are set of systems where there is no permanent dipole, still there can be a van der Waals interactions due to transient dipoles. So here we are talking about permanent dipole. Each molecule will have its permanent dipole all the time. Okay, like I said, example HF, HCl, water, and so on. So here, as I said, that there are atoms and molecules which will have a permanent dipole, and because of this, dipole-dipole interactions, which is an attractive interaction, occurs, and these energies are little bit stronger than the van der Waals interactions. You can see it can go all the way up to some 16 kilojoules per mole, 6 to 16 kilojoules per mole. We give a range because these interactions depend on how far molecules are, what are the dipole moments and all that. Again, you can compare this with the primary bond energies, which is of the order of 350 plus. Okay, so even dipole-dipole moment is still weaker compared to primary bonds, but stronger compared to van der Waals forces. And so if you need a sort of an expression to calculate dipole-dipole interactions, again we have theoretical derivation of these interactions. So as you can see here, it is proportional to the square of the dipole moment of each. Okay, so P1 and P2, these are the permanent dipole of the two atoms. If you are talking about like atoms, it becomes just P power 4. Okay, but if you have an unlike atom, you square the dipole moment of each and then you take multiplication. And then there are some other constants. This also goes as 1 by r power 6. Okay, and there is going to be a negative sign here, meaning it is an attractive dipole-dipole interactions. Scaling in the same way as that of van der Waals interactions, but the magnitude can be higher depending upon this, right? And if you see that, what makes this dipole-dipole interactions, interesting is that it depends on electron negativity of the participating pair. If you have a higher difference in the electron negativity of two atoms, you would have a higher dipole, and therefore you will have a higher dipole moment. Okay. So here, if you see here, I have given for some of the elements, I have given relative electronegativity value. So electronegativity basically tells you how strongly this atom is able to pull electrons. Okay. So you see this fluorine here has a very high electronegativity. That means it's a very strong electron puller compared to, let's say, hydrogen, which is 2.1. Okay. Now if you think about two bonds, think about CH bond or CF bond. Okay. So if you think about CH bond, the difference in the electronegativity is only 0.4. Okay, I got two atoms. Let's say it has a trying to interact. Okay, so between C and H, the electronegativity difference is only 0.4. Whereas if you look at carbon and fluorine, CF, between C and F pair, the difference is about 1.5. So therefore, you will see that the dipole moment interaction is going to be far more stronger for polymer with a CF bond compared to CH bond. Okay, so that's what I'm trying to say, that if you have a polyethylene polymer which is predominantly with a CH based bond, and it will have much lesser resistance to heat and temperature or even solvents at high temperature than Teflon. Teflon has a polymer which has a CF bonds. Okay, hydrogen is replaced with the fluorine, so you have CF. So between polyethylene and Teflon, you have a huge difference in the mechanical property. Teflon is very resistant to temperature. Polyethylene, on the other hand, it's easy to melt. It's very easy to dissolve also in a solvent. But Teflon is very resistant for chemical. You can spill acid, it'll be fine. You can heat it to high temperature, it'll be fine. Mainly because the CF bond is able to have very high dielectric, very high dipole moment, and the dipole-dipole interactions are very strong that keep the chain very together. And it's very difficult to make them go away from each other. Why I'm saying all this is because since we are talking about polymers and degradability and biopolymers, we have to understand at a molecular level what are the things that are important in dictating their chemical resistance, high temperature applications, and strength, and etc. Okay. So here we are showing this example that how dipole-dipole interactions can be very dominant between polymers. So here I have shown an example of two polymer chain made up of PVC, polyvinyl chloride. I will come to this chemistry of polymer later, a little bit later. So in polyvinyl chloride, what we have is, if you have a polyethylene, all of them are actually hydrogens. Okay. In polyvinyl chloride, you are going to replace one of the hydrogens with chlorine in an alternative fashion. Okay. This is based on vinyl chloride. So here I have two chains of polyvinyl chloride, and you can see that between HNCl, there is going to be a dipole-dipole interactions, because the electronegativity of hydrogen and chlorine is quite different. Okay, so the dipole-dipole interaction is going to be very strong. Similarly for the polyethylene versus CF. So these kind of dipole-dipole interactions are called Keesom interactions. Okay, in colloids and surface force literature, and you can also think about this kind of a formula that allows you to quantitatively calculate for a given pair of atoms with a different dipole moment what is the intermolecular force, right? So we are talking about primary bonds with which we can create chains. Once the chains are made, the chains are going to interact through various secondary interactions. We talked about van der Waals or dispersion interactions, which operates for all kinds of molecule, polar or non-polar, it's always there. Now there are some other classes where there is a permanent dipole, and those are interacting through the Keesom interactions or dipole-dipole interactions. And these dipole interactions energies are in the range of 6 to 16 kilojoules per mole, and you can make it stronger or weaker depending upon what is the electronegativity difference between the participating atoms. Okay, those are the key points to remember. Now, the third one is very important, that's called hydrogen bonding. Hydrogen bonding, we know that in water, ice, water, liquid water, this hydrogen bonding is very important. and that makes the properties quite different from the others, right? So you can think of this hydrogen bond as a special case of the dipole bond interactions, the one that we saw before. Okay, so we often say hydrogen bond whenever one of the participating atom is hydrogen and the other one is either oxygen or nitrogen or fluorine. Okay, so it's a subset of dipole-dipole interactions. Okay, and this can be a little bit stronger than the other secondary interactions. You can see it can go up to 30 kilojoules per mole. Again, 10 times lesser than the primary bond energy. Okay, but among the secondary interactions, the hydrogen bonding is something very strong. Okay, and that's because hydrogen has the least electronegativity compared to the other. So when you have H between H and O and H and N and H and F, you would have the largest electronegativity difference, thereby stronger dipole-dipole interaction. So we give a special name to that as a hydrogen bond. Okay. So here is an example. This is nylon 6,6, or it's called polyamide 6,6. So in the top, you have one chain of nylon. Here we have another nylon. So if you see here, we are only highlighting the interaction between H and O, H and O, H and O, H and O. You could also have between N and H and so and so. Okay, and these are called the hydrogen bonding interactions, and this is very, very important, especially for example nylon. We know nylon is a very strong fiber. So when you actually extrude this nylon as a fiber, you basically change the chain orientation in such a way that you enable this hydrogen bonding to be very strong. Okay, and therefore this fiber becomes very strong. Even though it's thin, it can be very strong. The same thing is applicable to silk fiber. So when a spider spins silk, it actually tries to extrude into a thin fiber, and during which time the silk fiber actually orients such a way that it actually maximizes the number of hydrogen bonds. Okay, when you have a higher number of hydrogen bonds, you have more strength. Yeah, so that means if you are thinking about a very strong polymer with the strong mechanical properties, you have to see how I can enhance hydrogen bonds, how I can enhance dipole moments, how I can enhance van der Waals interactions. Those are the choices you can make. And the last one is called induced dipole bonding or induced dipole interactions. So what this means is that we might have a situation where we have a pair of atoms. One atom is non-polar and the other one can be polar, having a dipole moment. So when these guys come together, the one that has this dipole moment can actually induce a dipole moment on the otherwise non-polar molecule. Okay, so one atom is inducing an electric dipole moment on the other one, again temporarily. Once you remove this atom will come back to non-polar state. Okay, so that's what I'm trying to show here, that you have an atom that is non-polar. Okay, there is no net dipole moment, but then if you try to bring another atom, another element having a dipole moment, and the electrostatic interactions through that can actually shift this electron a little bit away and create an induced dipole moment. If I remove this foreign atom, it will come back to this. Okay, so this is something called a induced dipole on a non-polar atom due to another neighboring atom, right? So that's what we see here. A polar molecule can induce dipole on a neighboring otherwise non-polar molecule. Okay, and this interaction is quite weak, and it can be one order less than the other intermolecular forces. So it is not very strong, it's very weak. And the interesting thing is this interaction also goes as 1 by r power 6. So pretty much all the secondary interactions or intermolecular interactions scale as 1 over r power 6, and they're all attractive. And you can see that it depends on the dipole moment of the neighboring molecule. Alpha is related to the electric polarizability of the non-polar molecule, and based on that this happens. And this interaction we call this as Debye interaction or induction interactions. Okay, so van der Waals forces or dispersion forces, dipole-dipole interactions or Keesom interactions, then we have hydrogen bonding, then we have this Debye interactions due to induced interactions. And there is one more possibility. Let me just summarize this. I am trying to summarize whatever we have just learned. We see that there are 4 different kinds of secondary or intermolecular interactions we talked about. It is not necessary that for a given pair only one of them should act. Actually, you can have combination of all the 4 is also possible depending upon the situation. Okay, so you can have one or more of the 4 intermolecular interactions operating between atoms, between chains, polymer chains. And if you even sum up all the interactions that are possible, you can probably go maximum up to 30-40 kilojoules per mole, which is still about 10 times smaller than the primary bond CC bond interactions. Okay, but you have to remember the chain is very long. Okay, so by making molecular weight longer and longer, bigger and bigger, you can also induce stronger and stronger secondary interactions. So molecular weight or the number of monomers in the system is also going to be very, very important. Now, these intermolecular interactions, even though we theoretically show all this, but in practical terms, how you measure or how you quantify is by looking at solubility in a solvent. Okay, so you take the polymer, put it in a solvent. If the polymer dissolves easily in the solvent, it means the interaction, the cohesive energy between these polymer chains are not very strong and is easy to disrupt by a solvent, right? So, and this intermolecular energy is important in determining chemical resistance that I already mentioned. So, if you want the polymer to be resistant to temperature, resistant to heat, resistant to chemical solvents, you want the chain to be interacting very strongly. Okay, and the way you can actually quantify this is to look at solubility, stability against temperature, and so on. And more importantly, like I said before, while the primary bonds are stable bonds and stronger bonds, and once broken, it's broken, but secondary bonds are not like that. These are actually transient bonds. You can break a hydrogen bond, you can make a hydrogen bond. You can actually make a dipole bond, you can break a dipole bond. Okay, it's a very transient thing because the energy involved are so less. By applying small amount of heat or changing conditions a little bit, you can switch on and off these interactions. Okay, these are all called physical interactions, modifiable. And one more thing that is common is something called cross-linking. Many times we add a foreign object to actually cross-link the polymers. This is over and above the secondary interactions. Okay, secondary interactions are there. It has some about 40 kilojoules per mole of level of interactions. But if it's not enough for you, if you want to literally link the polymer chains chemically, you add something called cross-linking agents. 2 examples. So here the green chain and the blue chain are basically natural rubber, okay, which is a polymer, and we add something called sulfur. Sulfur is a cross-linking agent. You can see this sulfur actually bonds between these chains here, and this ring can open and link to another chain. So it basically can actually link the polymer molecules in a 3-dimensional network, and these are strong bonds. These are not weak bonds, they are very strong bonds. In fact, the cross-link bond interactions can be as high as the primary bonds. Okay, so in many thermoset polymers, we use this kind of a cross-linking to have more stronger, thermally resistant, chemically resistant polymers. Okay, so rubber is one example. I am showing another example of bakelite or phenol formaldehyde resin, which is a thermoset. So here you can see that the vinyl group here cross-links the 2 phenyl groups here, the aromatic groups here. Okay, and then you can actually have another CH2 group from another chain cross-linking with this, and you can actually expand in a 3-dimensional network. So cross-linking always happens in a 3-dimensional way by linking molecules through a cross-linking agent, and these cross-links are as strong as the primary bonds. And it is said that it can have of the order of hundreds of kilojoules per mole, and it can be almost equal to primary bonds. Okay, so now this is fine. Okay, so from a molecular point of view, we understand how carbon is making bonds, primary bonds, how you can make chain, and then between chain, what are the possible interactions. That's all fine. But many times actually for practical reasons, if you want to quantify this, okay, you want to ask the question, what is the intermolecular forces between polyethylene chains or polystyrene chains? There are ways in which experimentally you can actually quantify this. Okay, so I'm trying to show some data here. Let me walk you through this. So there are two quantities that are commonly used to measure the intermolecular forces. One is called the cohesive energy density, which is called the CED, right? And this is given as the internal energy per unit volume. Okay, and it is also proportional to or equal to the square of the solubility parameter. Okay, so this is one way to calculate. The other one is called internal pressure. So this internal pressure is written as at a constant volume the derivative of internal energy with respect to volume. Okay, there is a mistake there. Yeah. Okay, so this should be, I think, temperature, but this is correct. So what it means is the difference between the cohesive energy density and internal pressure is simple. The cohesive energy density is written as this energy by volume, internal energy per unit volume, whereas the internal pressure is written as the derivative of the internal energy with respect to volume at constant temperature. Okay, so this is an absolute ratio of energy to volume, but this is looking at the slope of energy versus volume curve at a constant temperature, and these are actually experimentally measurable quantities. Okay, so the plot that I am showing here is kind of ranking polymers based on the cohesive energy density. So if you see here, so the values actually range from 300 to 650 joules per ml, joules per centimeter cube, that's a unit. And you can see that several kinds of polymers are listed here. So PVC is polyvinyl chloride, having very high cohesive energy density because what? Why do you think PVC would have such a high cohesive energy density or high amount of intermolecular forces? I had it in my slide. Yeah, it has a dipole. It had a very strong dipole moment, right, between H and Cl. So because of this very high dipole interactions, you have a high cohesive energy density here, right? But if you look at this other polymers like polyethylene, polypropylene, they are in the lower side, polypropylene and polyethylene. That's because it's only having CH. Okay, with the hydrogen and hydrogen, the van der Waals forces are weak. There is no dipole moments. There is no hydrogen bonding. It's actually rather weaker. Okay, so the polyethylenes, in general, olefins will have a very low amount of intermolecular forces. That's why they are very flexible, not thermally resistant, easy to dissolve in a solvent. Whereas PVC, as you see, is very strong. You can make pipes out of that, very sturdy pipes, because that dipole interactions are very strong in that. So therefore, whatever we are talking about in terms of intermolecular forces, it actually manifests itself in the mechanical properties. Okay, so that's what we are trying to see here. So polymers like non-polar polymers like polyolefins have very weak cohesive energy density or internal pressure, whereas other polymers like PVC, polyether sulfonate or polyacrylonitrile have very high cohesive energy density, mainly because it would have hydrogen bonding or dipole moment interactions more strongly. Okay, so in the case of polyacrylonitrile, there is a nitrogen component in there that enables hydrogen bonding and dipole interactions. PVC, as I mentioned already, is very strongly interacting through dipole interactions, right? And you can refer to this paper if you want to know more about how this is estimated. And you can see that this picture looks very similar, except a few exceptions. That's because the definition is slightly different. Okay, this is E by V, whereas this is the derivative of E with respect to derivative of V. Okay, And if you want to know how this is measured, as I said, what you can do is you can do an experiment called a constant volume thermometer, where you keep a constant volume, increase the temperature and look at the change in the pressure. Okay, and you get that. Once you get that derivative and multiply the temperature and subtract the pressure, then you get this internal pressure. Okay, so the details of this experimental details are there in this paper to see for you. Yeah. And one more point I want to highlight is that how this cohesive energy density can be manipulated by the chain length of the polymer. Okay, so here what they have done is they have calculated the cohesive energy density as well as the internal pressure. Okay, they are slightly different, but you can see the trend being the same. This is actually plotted 1 over n for set of n alkanes: propane, butane, pentane, decane, dodecane, and so on. So because these are basically CH3 CH3 groups, right? CH2 CH2 groups joined together. So if you look at this internal pressure and CD of n alkane, so here n means the number of methyl groups. Okay, so you would have longer alkanes in this side, shorter alkanes in this side. Okay, so when you increase the chain length from here to here of the alkane, the cohesive energy density increases. Okay, by making the chain longer and longer, you can make the intermolecular interactions stronger and stronger. And this is applicable to polymers also. Taking the same polymer but adding more units is another way of increasing the cohesive energy density, right? Okay, so I think that's all I have. So any questions at this point?